Hello, everyone. Thanks for joining us. We'll get started in just a moment. Hello to everyone who's just joining. The webinar will begin shortly. And hello, this is Leah Freeberg from Fluke Reliability, and thank you for joining us for this best practices webinar today. You probably know Fluke as a test tools provider, and you may also know that we produce some of the industry's favorite reliability tools, from infrared cameras to vibration meters. But you may not know that some of the measurements that our tools collect now flow automatically into EAM systems of record. It happens via a framework that we call Fluke Accelix. Our goal at Fluke Reliability is to better connect asset management data and teams with asset management systems to drive connected knowledge. And of course, that knowledge depends greatly on best practices in condition-based maintenance. So that's why this series of webinars explores reliability maintenance strategies, and that's why we feature speakers from a variety of expert backgrounds. I do have a few housekeeping notes to go over before we get started. Today's session is being recorded, so your phone lines will be muted to minimize background noise. We will, however, be answering questions both during the session and after the presentation during Q&A. So take a minute now and find the questions tool in the GoToWebinar dashboard. Feel free to please feel free to submit questions as we go, and I will share as many of your questions as time allows for our presenter to answer. If we have unanswered questions at the end, we will follow up with you. We will also be using the chat tool today for a different purpose, so find that tool as well. If you'd like to receive the slides from today's presentation, please let us know during the survey that will appear at the end of today's session. So don't hang up until the survey appears and you've answered the questions. We're also happy to send you a certificate of attendance after today's webinar. You'll see a question on the survey about getting a certificate, so answer yes to that one and we'll send it to you. A recording of this webinar will be available on the Accelix.com website within a day or two. And that's it for housekeeping. Now for the main event. Today, we are very pleased to have with us Blair Fraser, renowned reliability and IIoT technologist with UE Systems. He'll be presenting on gaining deep insight into bearing health with ultrasonic analysis. Blair is a technology evangelist dedicated to combining sound reliability principles and processes with the latest technology to improve asset performance and uptime for customers globally. He is the Global Director of IIoT Solutions at UE Systems Incorporated, and previously the co-founder and Chief Customer Officer at Quartic AI, a company focused on providing machine learning and artificial intelligence solutions for industrial use. Blair is a Certified Reliability Leader, CRL, and Certified Maintenance and Reliability Professional, CMRP, with more than 20 years of experience designing, commissioning, maintaining, and improving equipment processes for the manufacturing industry. Welcome, Blair. Thank you so much for being with us today.
Thank you, Leah. And it is always awkward to have your bio read in front of you. I'm not really sure what to do during those times, and it always reminds me I have to shorten it. But to summarize that, and thank you again, is, you know, I really focus on technology, but really combining that with the fundamental knowledge that I think we need as maintenance and reliability professionals. So as we're diving into this, and we're talking here about, you know, using ultrasound to be able to get a better understanding of what's happening in our bearings. So over the next hour, or hopefully a little bit less, you know, what I'm going to try to do is, I've had the pleasure of being able to look at hundreds and hundreds of bearings, looking at real-time data, the impact of under lubrication, over lubrication on some of the harshest environments that we have out there. And let's be honest, you know, from a bearing perspective, we have, you know, just a motor and a pump that spins in a circle that's pumping water, that's kind of the low-hanging fruit. That's a good application, but we have equipment out there that's in harsh environments. I'm going to show you examples of bearings on conveyors that get slammed in a pulp and paper mill with wood and plastic coming down these big containers, and what does that mean for the bearing, and how do we look at that data coming through? So a lot of this discussion we're having today is using real life examples. I'll give you the background. A lot of in fact, all the customer information of their names have been scrubbed for privacy concerns, but their data, they've given us permission to use their data as an example for us to learn from. So when I look at this, and from even in my spot as a technology person, right, we're now seeing, and there's nothing wrong with it, and I think we do need to address this, is we're, from a bearing perspective, we're spending a lot of effort trying to, identify a failure once it's happened, right? And really what I think we should start doing, and many of you might already be doing this, is how do we start looking at eliminating that defect from happening in the first place? Right. So when we look at specifically using ultrasound, now it doesn't matter which P to F curve you look at. When we look at that P, which is identified by Nolan Heaps back in the late 60s, it's an identifiable physical condition, right? So typically at that point P in the P to F curve, when we start to pick up with technology, something that's happening, there has to be a identifiable physical condition that something's happening, that something, is not normal. But if we can work, an ounce of prevention is worth a pound of cure, if we can work at eliminating that in the first place. And now what I'm going to talk about today is a major contributor from premature bearing failure, but it doesn't mean it's the end all. I personally believe there's no one technology that's going to solve all of our problems. And that's why the Fluke ecosystems like Accelix is there to bring in multiple data points into one system, and ultrasound being one of them. So when we look at, first of all, the power of ultrasound. Now, this dates back, and I would never ask any of you to read this study going back to a NASA study, because the main intent wasn't to prove ultrasound. It's a very long, boring read, but essentially over decades and decades. And what's interesting is, IoT is coming about in technology. More people are starting to leverage ultrasound, so we're seeing more and more. Specifically in academia, these theses and white papers come out about using ultrasound. And study after study, for decades, they've been able to show that, in a change in ultrasound, and I'll go over what ultrasound is in more detail, is it can pick up in incipient, or that initial early stage bearing fault before there's a change in vibration or temperature. And where this can be very good is obviously it gives you more warning, but where it can be very bad is the uncertainty and confidence you can have that there is something actually being wrong without being able to complement it with other technologies. And furthermore, when you look at vibration, there's clear standards, there's a lot of history with vibration, but with ultrasound, and in particular, when I'm talking about the overall values of decibels, what is a good bearing? What is a bad bearing? Because it's relative. So we have to start using our brains a little bit and some historical data to make these decisions. So when we look at ultrasound, so essentially what we're doing is, the way I like to just to describe it, and by all means, I am not, the ultrasound expert and going to go into the engineering concept of ultrasounds, but the way I like to describe it to my friends and family, because they still ask me, what do you do on a day-to-day basis, right? Is, we're listening. We're listening at a frequency that we can't hear, even dogs can't hear. We're going beyond that, and we're listening. In this case, from a bearing, we're looking at two things. We're looking at friction and we're looking at impacting. So we're looking at noise that's going to come from that bearing. And then we also have, and when I'm talking about bearings here, that's what we would call structure-borne ultrasound. So it's coming from a structure. It's not like a ultrasound where you would go and look at a baby in a mom's stomach or anything like that, right? This is different type of ultrasound. We also do have airborne ultrasound, which is really good at picking up turbulence and things like that for electrical faults on electrical equipment, valve leakage, steam traps, and things like that. But in this case, what we're doing is we're talking about friction, and friction ends up being one of the most important parameters I think we can measure in a bearing. And I'll go into why in just in a second here. So, I've laid out where ultrasound fits on the P to F curve, right? And this is, it's not ours, not UE systems P to F curve. This is just generally accepted in our industry that ultrasound will pick up a failure before any other change in vibration or temperature, right? With the faults that I've already gone through. And, people often ask me, what is better, vibration or ultrasound, right? And I always go back, what problem are you trying to solve, right? And I'm going to get a little more into that. So where the difference is in vibration, yes, we both use piezoelectric crystals, but how we use them is a little bit different. And in this case, whereas technology going is to MEM sensors, is from a vibration point of view, there's a mass on a spring, right? And essentially something has to move to generate that force to be able to get a corresponding. And I'm simplifying this. If there's anyone in the vibration world here, you might be have steam coming out of your ears because I'm doing injustice to explaining vibration, but that's not my intent here. But there are the way vibration is measured is around displacement or movement, where ultrasound is measuring a frequency or the sound coming from it, right? So different techniques, and there is some overlap in terms of of the benefits, but they are typically used to solve different problems, and they also fit into different maturity of your organizations as well. So what I'm going to do is I'm going to read this question out to you. I know most of you have already started reading it, which is typical in presentations, and this is why I hate putting too much text on there, but I'll summarize for you. Do you believe that there is value in identifying that there is a failure? In this context, I'll use a bearing, that there is a issue in this bearing that requires maintenance, therefore avoiding catastrophic failure, personal health and safety issues, downtime, even if you don't know the exact root cause. So if you don't know it's an inner race defect, an outer race defect, a lubrication issue, but there is something going on in this bearing, do you believe that there is still value from identifying that there is something wrong in this bearing without knowing the exact cause? Here's a preface: at that exact moment. It's not stopping you from doing a root cause or getting more information, but is there a benefit in knowing that there is something going wrong with this bearing? What I'll do, Leah, is I'll ask you if you can create that poll and share some information to me. That'd be great.
Okay, the poll is now open, and audience, you know what to do. I only have a portion of Blair's full explanation here, but even without identifying the exact cause of the fault, is there still value in identifying that maintenance is required? And you must select either yes or no. And as usual, I'd like to get about 75% of the audience contributing so that Blair has a sense of your feelings on this. And we are almost there. I'm going to give it about 5 more seconds. Click yes or no, and then I will share the response. There we go. Well done, everyone. Blair, 97% yes. They are with you on this. Only 3% no.
Good. And that's a good thing, or else it would be a really awkward rest of this discussion.
Right?
But for those 3% that didn't, I understand, and I agree with you. So it's a little bit devil's advocate. I agree with you that in order to improve, and the thing about reliability, and the fundamentalists are going to tell you that reliability cannot be improved through condition monitoring, right? You really have to re-engineer and eliminate those defects from coming in. You can realize the potential inherent reliability in an asset. So absolutely, in order to improve reliability, if you want to sit in the same race of just identifying, replacing, you're never going to get out of that race. You do need to do a root cause. You do need to get more information to essentially eliminate that defect from happening again. But where we see most people is just on the maturity, the amount of resources is the reality is we cannot do that for every single failure we have, and we have to prioritize and get operations or production up and running and things like that. So I do agree, but for the most part, that 97%, I would agree with that. Where we're at is just having that initial something is going wrong is very informational to us. And what we did is we started to look at at UE systems, we have been able to help our customers with, quote unquote, predictive maintenance using our handheld tools. So that's going around doing compressed air surveys for leaks, checking bearings, looking at electrical equipment, those type of things. And we looked at specifically from a bearing perspective, is what we found, and most customers do it on a monthly route based. Now, more critical assets might benefit from increased frequency, but what we found is on average 80 to 90% of the readings that were taken were on healthy working bearings, which is a great thing. It does two things. One is it gives you the certainty that this bearing is okay, and two, it allows you to use your other sensors. And in my opinion, as great as technology is going to be, there's still tremendous value in having a human, someone trained, someone skilled, walking the plant floor, looking at things technology can't pick up. And this is coming from a technology guy. Yes, we can put webcams in and things like that, but as far as I know, we still can't smell. Now on the PDF curve, if you smell something, it's pretty down that PDF curve, but there is still tremendous value. But this is the challenge that we're starting to see as it comes up in these IoT systems is, instead of us going to collect the data, can we bring enough data to us to make an actionable decision? And that decision might be to go to that bearing to take more data, which is fine, but at least you're starting to control when you go out to that bearing versus just doing on a time-based schedule. And then when we look at how bearings fail, right, it is no secret, and this is a study by SKF, but there's multiple studies out there by industry, by vendors that show similar results, that when bearings fail prematurely, lubrication is almost always the cause, right? So if you're looking for, if you have bearing failures, and this is over softfoot installation practices and things like that, they all get addressed in these studies, but they're a minimal impact. So if you have bearing failures, what would make sense to tackle first? Lubrication. So let me ask you this, and what we'll do is we'll use the chat feature in here just to get some people's responses and to get you thinking. I want to imagine this scenario where pick a bearing in your facility and you already have it in your mind. You get one question to ask it. What would you walk up and ask it? So I'll give you a few seconds here just to put your thoughts here in the chat, and I ask you to please put just whatever comes to your mind, whatever you think you would walk up to that asset and start to ask it, right? But you only get one question. There's no follow-ups, right? And as you're thinking about that, and whether you're putting in the chat or not, that's fine, but you have an answer for your head. And I can pretty much tell you what most people think from doing this question a lot is, one, when are you going to fail, right? Or how are you feeling today, right? In context of what we're talking about here, right? So I can tell you those are good questions to ask, but what I would challenge you is those are very selfish questions. You're thinking about you personally and that bearing in this case, right? Is what if we flip that question on its head? And imagine you're walking by and that bearing can capture you. And I'll just use some general names. Joe, Bob, Steve, you're walking by, right? It's like, hey, come here for a minute. This is the bearing talking. What do you think that bearing would ask you, right? Hey, buddy, what's causing you stress? Exactly. So imagine it can ask you a question. It's going to say, hey, right? I need a little grease here. I need a little help. It's getting a little friction-y in here. I don't think friction is an actual word. Or will you stop lubricating me? I have enough. I'm going to blow my seals, right? What type of lubrication and how frequently? Exactly. So I'm not asking you to change your mindset. And if you walk by an asset, it's really not going to ask you a question, or I don't want you to go out there and start talking to a bearing. But you can start to think how we can change our mindset. Instead of what the bearing can do for us, what can we do for the bearing? So I mentioned that ultrasound is measuring friction and impacting. Why is that so important? And I'm just talking specifically from a rolling element bearing. The concept is a little different with sleeve or driller bearing that rides in an oil bath, because if you have friction in one of those, you're too late, right? You have rubbing. Yes, you can detect it before you might have shaft damage and things like that. But specifically from a rolling element bearing, right? What can friction tell us? And I've been in this field for 20 years now, and I started as an electrician, as an asset owner. And I often joke, from a lubrication point of view, I feel like going back to my previous employers and apologizing because I was responsible for lubricating. And what did I do on a monthly lubrication route? I go lubricate, and I would just squeeze, right? Often I would squeeze until it came out, thinking that, hey, that bad grease has been in there, I need to get it out, right? And what I was doing was actually leading or causing that 80% of premature bearing failure. So as we start to, put more and more condition-based maintenance or predictive maintenance, what we're trying to do is do maintenance or interventions based on the condition. What is the most important condition of a rolling element bearing? It is friction. So if we start measuring that, we can tell a lot of things. First of all, what we can do is we can identify poor lubrication, right? And if that is 80% of what's causing bearing issues, and it's not just the quantity of lubrication, right? There's also contamination in the lubrication, over or under greasing, which in fact, by far, we see more over greasing. There's using the correct grease, all those other things apply to that 80%, right? But just by measuring friction, we can get a lot of information on that bearing. So when we look at what causes that 80%, right? Yes, there's material defects, there's indirect failures, there's improper mounting, which we've all seen those people with the biggest hammer possible smashing that bearing in. Even just the wrong bearing types, right, has a huge impact. But as we get to really what's causing that 80%, insufficient lubrication quantity. As I mentioned, over-greasing is often more detrimental to that bearing life than under-greasing, right? Long time without renewing, unsuitable lubrication, and lubricant contamination. So we've relied on time-based lubrication frequencies. Now there's a lot of different calculations out, which is going to bring you into the ballpark. But what is great, and what I mentioned about earlier, is we're asking our assets to do more in harsher environments, and often now in varying environments. So when you do these calculations, and you can see here N equals speed, what happens if I change the speed? More and more, we're moving away from controlling our process with valves, and we're putting variable speed drives in from energy efficiency. Or, I'm just based out of Toronto, and it's snowing today, but next week it's going to be short and t-shirt weather. How does that affect the life and the re-lubrication frequency of that bearing? Absolutely it does. So what we can start to do is let friction tell us when that grease is starting to not withstand its properties, when we need to refresh that grease, instead of assumptions, because that's what we're doing. These correction factors are assumptions, right, based on what we see as an average. But if this equipment's outside, absolutely temperature can have a big effect. Now, as I mentioned, there's not a lot of what I would call references or thresholds with ultrasound compared to vibration. Now, there is an ISO standard which dictates, if you have a bearing and you see an 8 decibel increase, and that's what ultrasound is doing, is measuring the decibel or that sound level of that friction impacting, indicates it needs lubrication. This is a hard written rule. Now, we may change that because it's a bearing wheel drive or something like that. We may increase it to 10 to cover all the operating differences with it. But generally these rules are true. And if it's 16, what we see is the early onset of failure. And this is where actually this early onset, as I mentioned, can be a little bit onerous, because it might give you too much notice. Like, well, I don't see anything with temperature. My temperature has increased or my vibration has increased. And that is true, right? But it is giving you idea that there's an increase. And then when we see a 35 decibel increase over that baseline, it means it's close to failure, and you will absolutely start to pick this up with other technologies, right? So these are the rules we base every decision on. But as you can see, it's based on a baseline. And what is challenging, and I will go over how I would recommend from my experience that you set these baselines, but no two bearings are manufactured the same, are installed the same, are greased the same. So the baselines can vary. And that's where the challenge comes in, of setting the proper baseline. So when I talk about using friction to be able to make actionable insights very easily on your bearing health, is once the baseline is established, and believe me, I will get in to how we set the baseline. right? And some methods we can do to make sure we're setting an accurate baseline, because the reality is when we install, and I'm holding up a sensor here, hopefully you guys can see it, when we install these sensors, very often they are on existing bearings that have been running for a long time, that, you know, the lubrication frequency, the health of them may be a little bit unknown, to say the least, right? So setting that baseline is important. So one of the ways we like to look at this is by a gauge widget. And what we do is we set those 8, 16, and 35 decibels, and we start to trend that over time, right? And this is a real time. So if you see this arrow, in this case, the baseline is 26, and it's reading 28.7 decibels. So we're in that green zone. We've been trending in that green zone. And you can imagine if you had to look at, you know, tens, hundreds, if not thousands of bearings in your facility, you could quickly glance through these, looking at the friction, saying this is in the green zone, this is a healthy bearing. In fact, do nothing, don't tinker with it, right? Just bask in its glory of being a healthy bearing, because chances are you're going to have that 10 to 20% of bearings that are not healthy. So if that arrow was in the blue zone, that's an indication that you need, that you need, oh, I hit too many buttons here, that you need to lubricate that bearing. Now, what's great is this is, oh, sorry, folks. I think it says, give me a notice, it's paused there. So this is an indication that you need to grease this bearing. Okay, so if that arrow, mind you, is, say it was right up at the 40 mark, is you need to grease that bearing. What is great is you're measuring that friction in real time. Now, we've had a product out called the Grease Caddy where it straps onto the grease gun and you start to monitor it, and you can actually listen and watch and trend those decibels as it's greasing. But this, you know, you can do anywhere. You can do on a phone. So imagine that arrow is straight up and it's at the 40 decibel mark. You start to squeeze grease in. What you'll see in real time is that arrow start to fall. I think I have to go this way to account for the backwards. So it's going to start to fall as you enter grease, because you're reducing that friction to get to that baseline. This is fundamentally what's changing the game on, you know, what we're calling prescriptive lubrication. And because now we can do this remotely, right? So you're restoring that friction. Now I'm going to show you some real life scenarios where it has restored, it went to baseline, great. I'm going to show you situations, which is very common, where you put grease in, the friction goes down, but guess what? It comes back up, right? That's an indication something is happening in that bearing. Lubrication is a great way to mask an issue in a bearing temporarily. Now, if that arrow was in the yellow zone, that's an indication it's starting to fail. And if it's in the red, that's a critical failure. So how simple is it to start to get insights from friction? I'm going to give you an example. Now I hold up the sensor. This is an example of a sensor installed on a cooling tower. You can see it's mounted external to the bearing, and it's essentially listening to that bearing, monitoring its lubrication requirements and friction 24/7. It never takes its ear off, right? Even if the asset's not running, it's starting up, it's listening all the time. Now, this is what I love to see when we put these systems out and I check in and 24 hours later, typically, I'm like, just let it run. I want to see what the friction trend is. If I see something like this, and what you're seeing, this is the friction trend, that blue squiggly line at the bottom is the friction trend over 24 hours. Now, what's hard to see is a green line behind that blue squiggly line. That's actually our baseline level, which I think is set about 8 decibels. The blue line above that is our need lubrication, and then our warning in yellow, and then our critical in red, okay? This is a bearing on a cooling tower, which is varying speed all the way from 10% up to 100% speed. It varies a lot in terms of speed, which we're going to address. Does friction change with speed? Okay, so we will get to that. This is what I love to see. Keep in mind, this is a variable speed drive on a belt-driven cooling tower. Okay, so this is what we love to see. This is not always what we see. So when we look at that healthy trend, if we were actually to look into it and look at it to a histogram, we do have these features available. I don't recommend you need to go and look at every trend from a histogram. This is my way of showing you that there's one common spot of the highest friction, within this case is from 9 to 9.5. Out of the 24 hours we're looking at that, you know, about 36% of them were in that range. And we have a nice curve or nice point on this histogram, right? Which means this is a healthy, there's a common point of high friction, which is great. There's no bouncing around, and I'll show you what this looks like when it's not a healthy bearing, and it becomes quite obvious. But as I said, wait, my assets are varying speed. How do I use technology like this to actually monitor the friction? And there's study after study, and I will admit, until I saw it myself, I did not agree with this. And there were some academia studies, and if you want them, I am more than happy to send you where they were in a controlled lab. But I didn't believe it. I said, there's no way, because if that bearing speed increases twice as fast, I'm going to see more friction. But it is true. In a healthy, well-lubricated bearing, the friction should not change dramatically. We will see small increases in that friction just inherently, even on a healthy, well-lubricated bearing. But it becomes so evident of an unhealthy bearing monitoring friction when speed changes. If the bearing's unhealthy, we will actually see it track the process. I can tell you, I'm like, you just increased your speed on that VFD, didn't you? Like, you did. How'd you know? Because I seen the friction increase, right? And it's no doubt, if you have a car and you start to drive, if you have an issue, you have that certain, speed where you start to go, you back it down a bit, and like, hey, got rid of the problem. You didn't get rid of the problem. You're just not magnifying that problem enough, right? And that exact same situation happens in our bearings. So one of the challenges we have, in a case of our system, we're taking this friction data, we're listening to that every minute, which is aggressive. Considering if you were taking it every month, now you're getting 1,440 readings a day. What do you do with that? This is on a conveyor. This conveyor, it has these plastic boxes full of these wood chips come down, and when they come down this conveyor, they bang, right? So not only are we going to pick up the friction impacting that bearing, but every time, these new baskets come down, and we've seen this in timber mills and all sorts of in steel mills, we're going to pick up inherent process noise as well. And this is what this trend looks like. And if you remember that nice blue trend I gave you, right? This is the reality. That other trend was on a cooling tower. It was perfect. What happens in the real world, right? This is that trend. Can you make heads or tails of this data? No. So what we do is we start to look at that data a little differently. Instead of looking at it individually from an every minute point of view, is we take a moving average. This is probably one of the most extreme cases I've ever seen, right? Where we've had, just because of the process, and this equipment actually starts and stops about every minute, every 2 minutes. So the duty has a big play, because obviously if it's off, the friction goes down. If it's on, the friction goes up, right? When we start to look at it from an averaging point of view, look at this trend now. Look how well it's been able to adopt and take out the extreme processes and duty, so the on-off of these bearings. Now, when I look at this bearing, I can take all that noise away. I'm looking at that friction in that bearing. And I'm understanding you're going to have some questions about this, and I'm going to go through some more real-life examples for you. So here we are. This is an air handler unit, and what you can see here is, we went, the baseline was set at 10 decibels. It went up to 15 decibels. Now, the thing about that 8 decibel increase over baseline, what we see now, because of the convenience, people can get an alert on their cell phone and actually hit a button, and through our smart loop feature, actually go and dispense automatically the right amount of grease to restore that friction. So people get 8 decibels. Oh, this is so cool, and I'm gonna hit the button. I'm gonna go do it right now. In fact, we have a great story of someone doing it while putting their son to bed, and which is great. But the reality is, it doesn't mean at 8 decibels that bearing is smoking and, oh my gosh, you need to go out there and lubricate it. It's the first sign. What is happening in that friction is that thin film of grease required on those rolling elements is starting to degrade, right? It's not an urgent need. Now, if it was a 20, 30 decibel increase, I would say, yeah, you probably want to get there sooner than later. But in this case, we only saw a 5 decibel increase, right? But why this is important is, you know what, this is great. This is the first time I've had this system. I want to go lubricate it, right? So what they did is they hit the smart lube feature and they put in grease, right? They put in some grease and they put in 15 cc's. Give you an idea, that is 2 teaspoons of grease. It's nothing considering how much grease you actually put in from a grease gun with one pump. Those beasts of grease guns, and I know there's electric ones now, which I'm a little scared of, because they can put in a lot of grease. They can get up to 10 to 15,000 psi. I'm in Toronto here. I can probably rocket grease to a lot of you wherever you guys are. So they put in 2 teaspoons of grease, and look at that immediate change in that friction. So we started off at 14 decibels. Now we're down to 11 decibels. So we saw a 3 decibel increase, but we also saw the peak to peak, which is an indication of the impacting start to decrease. And I got a great example of that, right? So this is what we're starting to see in an under lubricated bearing. Now it wasn't catastrophically under lubricated, right? It gradually went up by that 5 decibels. We applied some 2 teaspoons of grease, and we saw not only the friction increase, but also the peak to peak, or that impacting, right? So this is a great scenario. You know, it was a little bit aggressive to go and lubricate, but since it was a new technology, they wanted to do it. So looking at that histogram, you know, is you can see here on the left-hand image, you know, there wasn't one central peak. And in fact, the ones to the right and left are actually pretty close. After lubrication, we had that nice central peak in there. So we're saying, you know, we reduced the friction, but we also got rid of that peak to peak, or that impacting in that bearing. So let's take another one, right? And this is another example. And what I want to show you is actually, I'll walk you through what you're looking at here. So this is a screen capture from our cloud-based platform called UE Insights. On the left-hand side, the graph, we're seeing those 4 levels of the baseline. The blue line is need lubrication. The yellow line is early warning, and the red line is critical. On the right-hand side, you're going to see that gauge widget, which I already explained to you. The widget to the right of it is actually the historical amount of grease that was used. So what's very important in a lubrication program is knowing how much grease you've used, who greased it, when, but we also record the starting friction level, the ending friction level, and the baseline for you, so you can start to do reporting on this is how much grease I've used in this bearing over the last year, 2 years, and things like that. And then below it, what you're going to see is what we call our cartridge widget. One of the issues with these single point lubricators is they don't have communication. So you had to rely on, you know, literally creating a scheduled time-based predictive PM schedule to go check these lubricators that are out there. Is the battery still alive? Do I still have grease left in them? Because we're talking to these devices, and it's called the MUE lubricator, we know exactly how much grease is left, right? So when we go to lubricate, we have confidence knowing that there's grease available. And I can, you know, go off topic here, but we actually have confidence that grease is getting to the bearing because we're monitoring friction. We have a back pressure to make sure that sometimes, you know, grease or bearings won't accept the grease because the grease lines are plugged up, or there's other stuff in the way, or someone disconnected it because of maintenance and didn't reconnected it, which happens quite frequently. And then on the right of that is the Smart Lube features, which if you put Smart Lube Assist in, which in this case they did, it's going to automatically grease that bearing, looking at the friction as its guide to how much grease to apply. So what happened was, you can see the steady increase of this friction of this blue line. And what happened here, it got above that line. They said, hey, let's go lubricate this. And I said, that's great, you go lubricate it. And what they did is they hit the button. As you can see here, now this is a 24-hour time frame. You know, if you were to zoom in on this spot, it actually probably was over about a half an hour. We used 9 cc's of grease, which is even less than a teaspoon, right? So not a lot of grease, and it's always remarkable how much grease we actually need to use to maintain that friction in the bearing. So it put that 9 cc's of grease in, and you know, we were at 22.1, and it got that friction down to 12.6. So we almost reduced it by half. You know, this is a great example. What's important to note here is the friction went down and it stayed down. That's very important. It's not just what happens as we're lubricating, it's also what happens after the fact. So here's another example. This wasn't a smart lube. They actually walked out with the grease gun and went and lubricated it. Now, did it warrant it? No, it wasn't above that blue line. We didn't see a big decrease or increase in the friction. But the minute they did it and they were looking at their cell phone while doing it and they went squeeze, they're like, look it, right? Is it updated, right? So this is typically what we see. And you'll also note, just look at what happened here. You'll see this, and you'll see the peaks and valleys of this. It's spiky, right? The minute grease hit there, you can imagine if you were listening to that bearing or thinking about what's happening in that bearing, right? That grease just smoothed it out. It reduced the friction and it smoothed all those peaks and valleys out. This is what I call the aha moment when you're monitoring ultrasound for the first time in real time and you go and lubricate and you've only put in a quarter of what you normally would, and you have to stop and you look at this trend, and I just wait for it. I'm like, oh, right? Here's another example. Again, did not warrant any grease, but what they noticed was this impacting. They put grease in here at this point, and look how smooth. It did reduce by maybe 1 or 2 decibels, but just look at the impacting change after grease hit that bearing, right? So if we want to do everything we can to maintain the health of our bearings, knowing that 80% is caused by lubrication, doesn't this seem obvious? So here's another example, under lubricated bearing, right? Again, in this case, 7 cc's. And I invite you to I have to do this every time because I've never worked in cc's. I've worked in grams, and many of you have that have gone out and lubricated. So I always do the conversion in my head. But you can start to see this impact, boom. And what I'm always surprised is how quickly that friction drops once grease hits the bearing. In fact, if you were to zoom in here, I'm not going to get any closer to the screen or else you'll look up my nose, but you'll see what actually happens is the first time grease hits the bearing, because it typically goes in the top and the rolling elements have to push it through, you'll see a temporary spike just for a second or two. It'll go boink, and then it'll start to come down, right? And in this case, we started at 29, we ended up with 16. This is a great lubrication. Now, before I get into the bad bearings, what I want to do is just see if there's any questions that can come up specifically related to an under lubricated bearing, just to give you a chance to address these questions before we dive into what a bad bearing looks like. So Leah, is there any questions that you think fit well with what I've talked about here with specifically a bad bearing?
Yeah, I'm gonna bring one up for you. You've done a great job of anticipating a lot of the questions that have come in. But here's one for you from Bob just a minute ago. It says, on the left-hand side of slide 27, the onset of the increase in friction seems fairly abrupt. Is this common, or is it diagnostic of a specific problem?
Great question. Great question. So typically, if it's a lubrication issue, it's a slow, gradual, sustained increase in friction. So this is typically, if you see a sudden rise, it can either be operation driven or there's a defect in that bearing. Now, it's not to say that we haven't seen, relatively aggressive, because the way the grease type started to degrade. And it depends on the grease type, if a lithium complex and stuff like that. It'll actually have different rates at which the friction will go. But if it's really abrupt, like within an hour, you're like, whoa, it was fine. And then last time I looked at it and I looked at it an hour later and there's an increase, it is an indication, in my opinion. This isn't, to write a blanket statement, because, we've seen everything different ways, but it generally, I'd expect a slower increase in friction.
Good. There continue to be questions about baselines, and I know you're going to continue to address
That's
that.
right.
And there are also questions about what do you do with a VSD,
Yes.
right? And so I'll put that in your awareness so that you can
Please
address
do.
it as you come up.
Well, that was very good timing, because what we're looking at is a VFD or a VSD, a variable speed or variable frequency drive.
Mm-hmm.
So if you remember, and I'll get back into this presentation now, thank you, Leah, is when we look at this, you do not have to be a PhD to be able to understand this trend from the information I've already given you, right? Is that green line's our baseline. You can see this is an air handler unit. You can see that friction track with every move of that VFD, right? So this is not a healthy bearing. Do I know what the exact cause of this is? I do not. And what I recommended to them was, I would recommend you go out there either with an ultra probe where you can record a sound file, listen more in depth into that, or if you have a vibration, go take vibration data, because chances are if something is this bad, you will start to see it in other technologies. So to answer the question about, how do you deal with VFDs and the ISO standards with setting the alert limits, is what we may do is, because we might see a 2 to 3 decibel increase depending on the speed range of friction from what's on low speed to high speed. So what we'll actually do is we want to cover the alerts, whether it's operating at low or high speeds. right? So, once the train of thought is, well, I'm going to set my alerts only when it's in high speed, but what if that asset needs lubrication and only runs in low speed for the next week, right? Will you be able to catch it? So what we do is we'll actually play with those alert limits a little bit. So instead of doing 8 decibels, we might change it to 10 decibels so that we're not going to get any false positives on the high end, but make sure when it's in low, we still be able to catch it. And again, that 8 decibel doesn't mean that you have to take immediate action. It's the first notification, right? And what I mentioned was the lubrication is typically a slower rise in friction and sustained, right? So as you notice here, you're not seeing a sustained increase in the friction. So we'll play with those alert limits a bit to make sure we cover all operating ranges. So instead of using 8, we might use 10. Instead of using 16, we might use 18, right? And we can play with those numbers a little bit, being aware of the operating conditions and the current health of those bearings, right? So what you'll see in this trend here is this is tracking with the speed. This is not a healthy bearing, okay? It doesn't mean it's going to fail tomorrow. In fact, I believe this one is running still a month and a half later. We're monitoring it, and I'm zoomed out here, but even at the worst peak, we're still just going above that needs lubrication. I have seen them just go completely off the scale, which is more concerning, right? And this is an example of a bad bearing. Now, on first look at looking at this, and I should have shown, I could probably zoom out. If anyone wants to see this data live, I'm more than happy to show you. We can actually go around and look at the historical data. You would see a slow gradual increases. You can see here, they put 12 cc's. In fact, every squiggly line, what we do is instead of taking data every minute, we take data every second while it's lubricating to get that real-time feedback. So any condensed lines here is when they've tried to lubricate. So they lubricated it. It's trying to get it down to baseline. But it stopped. It said, hey, it automatically stopped. Because what can happen if there's a defect in that bearing, it will bring that friction down, and then whether we're over greasing it, so if we start to apply more grease, obviously the bearings don't have enough room to move in that, and it has to push through that grease, that friction will actually increase. So why it stopped here says, I'm trying to get down to that baseline of whatever it is, 2 decibels, but I couldn't do it. What I noticed was I started to get my friction to increase. In fact, what happened was, you can see it got down here, it stopped, it warned the user saying, I was not able to get this down to baseline. I had to stop because my friction started to increase, which is an indication we're over greasing or there's an anomaly or a defect in that bearing, which this does happen. In fact, they tried in this next squiggly line here, they tried to lubricate again. They said, no, try again. Maybe something happened, right? And it did the same thing. As you can see, that friction did not increase, right? So this is an indication that there's something happening with that bearing. Now, it could be that the baseline was set incorrectly, right? Which if and we always help our customers set the baselines, help review their data to get a more historical look at bearings, having looked at hundreds of these bearings on different applications, right? But in this case, it really was, there was a defect in this bearing that was stopping the friction from getting to baseline. Okay, so it doesn't mean it's a catastrophically bad bearing, it just means that it's a bad bearing. So here's another one. Look at this, right? And there's a reason why I cropped this image off on the right-hand side. You can start to guess what's going to happen. If I was to send you this image, you're going to say, this system worked great. And in fact, it did. It applied 4.5 cc's 14 days ago, and it got it down to baseline. Hallelujah. This system is amazing. Or this bearing is healthy. Okay. Now, if I show you what actually happened and I show you that full picture, what happened? Yes, that friction got restored for about an hour and a half. And guess what? It started to come back up again. It started to creep back up. What does that tell us? There's something wrong in that bearing that's causing that friction to increase, right? In fact, you can see we went over the critical. This is an unhealthy bearing. It did not sustain its friction level, which is very common. Now you think about what we used to do with route-based. We would go out there and we would listen to it. We wouldn't stand there for an hour to make sure that friction never got up, an hour and a half. Like, yeah, I got it down, and I'd walk away. You didn't have any other insights until you went back out the next month. And maybe you caught it, in one of these dips, which is possible, process related, right? Or maybe caught one of those peaks, right? But this gives us a new insight of how to look at this. Again, here's another one, right? Multiple lubrications, multiple days apart. So this is that same bearing, same trend. A few days later, they applied more grease. Yes, it got it down. It got it down for maybe 20 minutes and it went back up. This is the exact same bearing a few days later, right? So what we're doing is we're nursing that bearing. Yes, we're spending time on grease. Yes, in this case, it has a seal on one side, so the excess bearings just can get pushed out. It's a waste of grease, but from an operations point of view, we want to make this bearing last until their planned shutdown. So they're going to keep on doing this, knowing there's an issue with this bearing, but they are going to limp along, try to save as much life as they can in that bearing by applying grease and keeping that friction in check. Right? So again, we look at a bad bearing, looking at these histograms, these are nasty histograms, right? When we look at a notable increase in friction over 4 days, the peak to peak values are big and there's no single point, right? There's no common friction level through all operating conditions of that bearing. So I'm going to spend a few minutes here. I do want to leave some time for more questions at the end. So how do we set this baseline? Everything I've talked about is dependent on setting a good baseline. By far, and what the Smart Lube feature allows us to do is use what we call set while lubricating. And we apply a small amount of grease. In fact, our lubricators, if you have Smart Lube, we can do this by, like I just did one over the pond, if you will, in Europe this morning, is, we can control when and how much grease gets applied. So we put in 0.3 cc's, which is, it's a dropper of grease, right? And what we like to do is put a little bit of grease into that, right? And we might have to put more than 0.3 cc in, but what we see, if we see the friction start to reduce, it was under greased, right? And we'll start to actually apply it till, typically I recommend doing this manually for the first time, apply it until that friction starts to rise, right? And then, it's a good indication we can set our baseline. As we've seen, I let it sit there for maybe 24 hours, make sure that friction doesn't creep back up on me. If the friction increased from the moment we put grease into that bearing, if the friction goes boink, it starts to go up, that bearing was already over lubricated. In that case, we have to go to historical to set that baseline. And the friction remains constant, which is common. There's no signs of impacting, so we're not seeing these big peaks and valleys. And typically what I'll do at that point is I'll look at the historical, I'll make sure I'll trend that value, looking at all the historical, or making sure I capture all of the operating conditions of that. We'll let it rest there, and then we can go back with the level of confidence over 30 days to make sure. The other thing we can do, and I have some great examples of this as well, is comparing like for like of the same load, same type of bearing, saying, well, this one's running at 20 decibels and this one's running at 10, right? And if you remember the 5 whys, is funny, I have a certain set of questions I've asked, like, what do you think the health of that bearing is, or how you've been treating that? Well, yeah, that one I replaced 2 weeks ago, and that one's just holding on, right? And typically that one that's holding on is the higher friction. So we use these different methods of setting the baseline to our advantage. And the thing to note here is the bearing, it's okay to change that baseline from what you've learned. Okay, it's not set in stone. So obviously when you replace that bearing, it should be within reason of the previous bearing, maybe 2 to 5 decibel difference, but you will have to change that baseline, which is a good thing because hopefully that new bearing has a new friction profile, right? And I have examples of all of these that we can start to show. In fact, we have a live system in our New York office where we can clean out all the grease. We put in eco-friendly now brake cleaner, because the first time we used brake cleaner, we evacuated our whole office. So we can actually flush a bearing, put grease in, we can overfill that bearing to see what the trend looks like. And it's always interesting to see the first reactions of what happens when we're looking at setting these baselines. Now, the reality is I could go into a whole another hour webinar of setting these baselines, and we have a team dedicated that literally sits there and looks at squiggly lines, understands your assets, and will help you set these baselines. So how can we make it easy? So the first thing I look for is look for a consistent average trend value, right? Even in that case, that extreme case where these plastic cases are coming down on a conveyor and literally smashing into things, we have ways to make it analyze that data to look at that bearing friction only, right? We can get away from the duty and extreme loads. We're looking for peaks and valleys, which is indication of impacting, right? And this trend is a great example. You can have a good friction but bad impacting, right? And it can be lubricator related. It can be, going back to improper bearing selection. We've seen that a lot. So there can be many reasons why we're seeing impacting in the bearing. And then also look for an increase in friction over 30 days, right? The reality is the L10 life of a bearing is a lot longer than 30 days, right? And in a healthy, well-installed, lubricated bearing, we shouldn't see changes, right? In fact, when we install these systems, people get disappointed because nothing's happening. It's been treading the same friction. I'm like, that's a good thing, right? That's a good thing. We want your bearings to be happy, but they're just really anxious to pick up a win or be able to lubricate, right? In fact, we've had one customer to date actually go out and purposely flush their bearings with the grease just so they can put it back in and watch the friction trend. It's up to you. That's a way of doing it to prove the value. But those are the three main things we start to look for when we're looking at monitoring that friction in the bearing to make informed decisions of how we're going to maintain, proactively ensure the life of that bearing. So what I'll do here, you see my email here. By all means, connect to me directly, agree, disagree, want some more insights. If you do want to skip the middleman and go in, I want to see this system running live with live data. There's a Calendly link. What you get to do is pick a time on your calendar when we're available to walk you through a live demo. And if you do want more information, you go to uesystems.com/smartlube, and we will drown you with information on it and things like that. So what I'll do is I'll open it up, Leah, if we can open up to some questions here. I'll try to answer as many as possible.
Yes, thank you. And agreed, folks, you are welcome to follow up directly with Blair as well as using the demo link. The good news, Blair, is that we have a ton of questions. Obviously, the bad news is we will not get to all of them. More good news, however, we are doing our best to answer as many as we can right now. So keep putting those questions in there. We'll answer them via the tool. If not, we'll follow up with you afterward, okay? So continue to flood the system. We will get to you one way or another. I'm going to ask a couple that seem to be the most representative right now. Here's one that's sort of a summary question. How do you distinguish between issues in the quality of bearings versus the actual issues?
Yeah. So, I mean, regardless, those are issues, those are defects. And for the first time ever, I believe we've been able to identify a counterfeit bearing. It was an SKF bearing. And, we started digging in, where do these come from? I got these kind of on the black market, if you will. So at the end of the day, a defect's a defect, right? And again, it had to be root caused and out, but the same, whether it's a quality in the bearing, we'll see that same type of pattern as if a single rolling element has an issue with it or anything like that. Now, what we can see and what we've seen with wrong types of bearings, and as I was mentioning, on a properly specified bearing, the friction shouldn't increase very rapidly, but on if someone's using a thrust bearing, when they use a different bearing, what we'll see is the acceleration of that friction, indicating it could be possibly an incorrect bearing application as well. So again, it all comes down to looking at that friction and having some kind of history on that bearing itself.
Okay. Again, there's so many questions here that it's a bit tricky to find the ones that are the most representative of this, right?
But I will commit to answering all these questions either offline or however we want to do it.
Okay. And again, I'm also trying to interpret a couple of these. So I feel like you have answered quite a few of these in the flow of the presentation. Will the system continue to monitor and grease a bad bearing?
Great question. I feel that was almost a tee up, but it wasn't. This wasn't planned. So no. So when the system's looking at applying grease, first of all, it's going to do, before it puts in a single ounce of grease, it's actually 5 checks, but it's going to do these checks to ensure before every, what I call an interval of grease, right? So first of all, it's going to check to make sure grease is required. You can hit the automatic button and it's going to say, no, I don't need to, I'm at my baseline. What are you thinking, right? Why am I going to put grease in? So it's not just going to say you push the button and push grease in. There is a manual button. Every time you push it, it's like a manual override, it will dispense grease. But in the assisted or automatic mode, it's going to check to make sure grease is required, so make sure there is a delta in the friction. it's going to make sure that the cartridge has enough grease. We don't want to sit there running thinking you're putting grease in. It's going to say, no, dummy, this is empty, right? It's going to use different terminology than that, right? And it's going to check to make sure it's going to store every time it's put grease in what the friction change was. So if it sees that friction start to increase, right, it's never going to put more grease in, indicating there's a defect or where we're starting to overfill that. And what happens? So what happens if, you know, this is mounted remotely to the bearing and you have grease lines coming in? What if someone, as I mentioned, puts the grease line off, right? And you're monitoring friction, and hey, some of these cartridges can get up to 250 milliliters or 500 milliliters or 500 cc's. We don't want it sitting there dumping an entire reservoir onto the floor, right? And then you got to scoop the grease up, and please don't reuse it, right? So we actually store the max bearing capacity, cavity capacity as well. So under no circumstances in automatic mode, you can override it with manual, will it ever overfill that bearing, okay? It's going to say, nope, I'm done. I've overfilled this bearing. I do not want to blow these seals out. You can do it by all means by doing it in manual mode, but it's going to stop there as well, right? So there's all these checks in place around lubrication best practices that are built into the automatic mode. The idea was you hit the button, you walk away, and you have certainty. It's not going to blow seals out. It's not going to put grease on the floor and grease is hitting that bearing.
Very good. We have reached the top of the hour and we have a couple of slides to go through. Blair, if I can have you forward to the next slide. Excellent. All right, we're going to switch modalities for our next webinar on May 5th. We're going to be talking thermography. We'll be joined by Craig Haas. He's a thermal imaging expert with Fluke Process Instruments. And from those of you who know the Raytech days, these folks have been doing thermal monitoring before the IIoT was a thing. Sorry, Blair. And they've got a lot of data and applications. So I hope you'll all tune in for, again, the thermography portion of this, and specifically thermal monitoring and how it's being used for reliability-centered maintenance. So check the Excelix website for more information. And then if you'll forward one more slide, please stay online for a moment after I close the webinar. There'll be a brief pause, and then you'll see a survey link up here. We really appreciate it if you can take just a moment and answer those questions, because your feedback helps keep this webinar content relevant and helpful. Plus, there's that question on there about, do you want a certificate or a copy of today's presentation, and we will send those to you. This recorded webinar will be available on excelix.com within a day or two. If you want to share your certificates on LinkedIn, please do. Tag Blair and I and Fluke Reliability so we can cheer you on. And that concludes today's presentation. So thank you for joining us, Blair. It was such a pleasure having you on the show today. The audience,
My pleasure.
Audience, you were great, right? So excellent, excellent work. Okay, we will see you all next time, and have a great day.